Hello, everyone. My name is Ben Chow, and I study differential geometry at UC San Diego. And welcome to the Lean Learning Seminar. I'm co-organizing the seminar with my colleague Zulu Ma at the University of Tennessee, Knoxville. And we're honored to have a wonderful list of speakers. And I will now hand off the introduction to Zulu, who will introduce our first esteemed speaker.
Okay, thank you. So we're very honored to have our first speaker, Professor Kevin Buzzard from Imperial College London. He will talk about what is formalization and why does it matter. Okay, thank you, Kevin.
Right, hello. Thank you very much for the invitation. And sorry, sorry to get you all up so early. It's 4 p.m. where I am, but still. Uh, so I was told that somehow maybe one of the reasons this seminar has appeared is because at least some of you are thinking about formalizing a proof of the Poincare conjecture, uh, which I think is a terrific idea, but there's also a very large project. Um, So I was asked to give some kind of overview of things. So uh, I there's this talk's got three sections. Firstly, what is formalization? Secondly, why should one formalize the Poincare conjecture? Or more generally, why should one formalize any piece of mathematics? Uh, and thirdly, how hard will it actually be to formalize the Poincare conjecture? Uh, So, um, and I should say that I'm an algebraic number theorist by training. So I know some algebraic number theory, but I know next to nothing about the details of what goes into a proof of the Poincare conjecture. But I do know something about formalization. I've been formalizing mathematics for 8 years now. My goodness me. Um, so basically, I'm the point of this talk is I give you some of my experience. I've watched other people formalize things and sometimes big things, and uh, this is, I try to figure out what I should tell people who might be about to embark on formalizing a big project. But somehow I also want to say something about people that don't really know anything about, anything about the area at all. So I'm going to start with what's formalization. Uh, and this is using an interactive theorem prover to do mathematics. So what's an interactive theorem prover? It's very simple. It's a computer program that just knows the axioms of mathematics and the rules of logic. So in particular, it's not something that can magically do mathematics by itself. It would be like sort of it would be like writing a computer program that just knows the rules of chess. And it wouldn't play you at chess, but if two people wanted to play chess, then you could use the computer as a board. And if you tried to make an illegal move, it just wouldn't let you do it. It's just basically checking that all the moves are legal. So it's that kind of thing. This thing, it knows the rules, it knows the axioms of maths and the rules of logic. So it knows, it knows what mathematics is, but is not claiming it can do it itself. But it can certainly check if you're doing it correctly. So there's many such systems, and some have been around for decades. And there's the names of some of the systems. And formalization of mathematics is the art of teaching mathematical definitions and theorems to such a system. And it is an art. It's not just a purely scientific process, because there's somehow, you have to learn the sort of the ins and outs of the system you choose, and then you have to sort of manipulate the material. At the end of the day, you're using a foundational material, and so you have to understand how abstract mathematics fits into the foundations. And this is something that mathematicians have got quite good at over the last few years. And in particular, the lean community is the one that somehow has really taken off. And there's a large group of volunteers working on a huge mathematics library called MathLib. And I'm going to promote MathLib. That's because I'm a maintainer of Math. So disclaimer, I'm a maintainer of this maths library. This is a free and open source project. And right now it contains nearly all of an undergraduate degree, but not quite all, and a whole bunch of far harder stuff. So that's what's in this basic mathematics library that that comes with Lean, as it were. so if you want to do undergraduate level stuff, then that's fine. We've basically got you covered. If you want to do harder stuff, then we need to have a conversation. But let's start with the undergraduate stuff, because I'm assuming that there are people who might watch this seminar who haven't got a clue, who's interested, they might be interested in Ricci flow or something, but they might have never seen a theorem proof before. So what does formalization of mathematics look like? So let me drag this thing over here. It looks like this. Can you all see my screen? I'm hoping that I'm sharing a screen and that, okay, I'm getting a thumbs up. So this first line here means like import all of Lean's, all of MathLib's. So MathLib is the name of the maths library. Import all of MathLib's tactics. The system itself is called Lean. It's a programming language, but there's a big mathematics library on top of it. And the first thing I'm doing is I'm importing all of this maths library's tactics. And as well as doing that, I've just also imported a whole bunch of mathematics. So in particular, for example, core Lean by itself, it knows the axioms of maths, but it doesn't know what a topological space is. It's the job of the maths library, not the core system, to supply the definition of a topological space. So this says, let X, Y, and Z be topological spaces. So the green lines are comments, and this says let F from X to Y, and G from Y to Z be functions. I mean, it doesn't say that yet because I didn't do G yet. G from Y to Z. There we go. But I didn't say they were continuous. So what I'm going to prove, this theorem. I'm going to prove that if F and G are continuous, and so is G composed with F. So I should apologize in advance. I have a bunch of standard routines for showing formalization of mathematics to mathematicians. And this is one of many things I have up my sleeve, but if you've seen this one before, then apologies. So let's try and formalize what that says. So let's assume the hypothesis HF that F is continuous. And let's assume the hypothesis HG that G is continuous there, because F and G were just arbitrary functions before this point. And my conclusion after the colon is what? G composed with F is continuous. And now I type the word sorry, and now there's the setup. So now that was creating the level, right? This is a puzzle. This software turns mathematics into a puzzle game. I've just made a level of the game, and you can see the level of the game over here on the right. Let me bump up the. There we go. Let me bump up the font size, and I'm going to be typing in code on the left. That's where I'm playing the game. And here you can see Lean's brain. That's what's going on the right. And Lean's brain, the idea is it knows, this is everything it knows about the question. That funny little symbol there, this logic symbol, as anyone on the 7th floor at UC Berkeley will tell you, this means the thing after it is that's what we're trying to prove, and the thing and everything above it is what we know. So the idea is we know that X and Y and Z are topological spaces. We know that F and G are functions. We know that F is continuous and G is continuous, and we're trying to prove the composite is continuous. So great. How do we do this? And when we learn this in our first topology course, the first thing, of course, the question is, what's the definition of continuous? So let's rewrite the definition of continuous. So that's going to be called continuous def. Let's rewrite that everywhere. Yeah, so that's my first move in this proof. Let's replace the word continuous with its definition. And now you can see the state of the brain has changed. You see, I can move my cursor. That's before we ran that tactic. And that's after we've run the tactic. And now this sort of says for all sets, if something's open, then something else is open, right? That's the definition of what it means for a function between topological spaces to be continuous. So that's great. But you see, the computer isn't magically proving it by itself, right? I'm proving it manually. So now what? So now let's say, so what is the proof? We've got let's say we've got U living in Z is an open set there. So I know how to translate that into this computer language. So this is intro UHU there. So U is so now you see U is a subset of Z. That's the slightly weird way of saying that U is a subset of Z. And this new hypothesis, that wasn't there before. You see, that's just appeared. That wasn't there before, but now it's there. So now we've got this hypothesis that U is open, and now we've got to prove that the pre-image of U under G composed with F is also open. Okay, so you see that I don't have to write what we need to prove because the system is keeping track. And how do we prove this? Well, I guess the standard way we prove this is the first thing. We could let V, I guess we've got an open set in Z, we pull it back to Y. Let's let V, let V be the pre-image of V be the pre-image of U in Y, right? Let's do that. So how do I say that in that language? That would be let V would be the pre-image of that would be the pre-image of U, the pre-image of U. There, that should work. There. So now V is defined to be the pre-image of U. And I should, like, often mathematicians just write G inverse for pre-image, right? Do you see I've got this funny prime here? But G inverse in lean is used to mean inverse in groups, right? So pre-image of a set under a function, that's not inverse in a group sense, it's inverse in a different sense, and mathematicians overload that notation. But in lean, somehow we don't want to confuse, like G could be an element of a group, right? If G was a bijection and Y equaled Z, then G would be a bijection from Y to itself, and bijections from a set to itself form a group. So you could kind of imagine that the system would get confused if I started talking about inverses, because so this inverse primed means pre-image of a subset under a function. So V is the pre-image of U in Y. You see, this is the kind of thing you get when you formalize. You have to be sort of super precise about everything. And now I claim that V is open, right? Why is V open? That's because G is continuous, right? So have HV. I claim that is open V. And why is that? Why is V open? So I guess I need to apply the fact that G was continuous, and the fact that G is continuous is called HG. So let's apply that hypothesis HG. And now what have I got to do? And now the computer is saying, okay, you're claiming that it follows from continuity of G, but now you need to prove that U is open. You see, now we've got this temporary goal to prove that U is open. But that's one of our hypotheses. You see, hypothesis HU is the hypothesis that U is open. So we could go, that's an assumption. So we could type assumption here. There we go. And now that error is because I'm saying sorry. Sorry means I'm skipping the proof, but I don't need to say sorry because I've proved it. So you see, we can go on very slowly like this. Let me just I mean, we're halfway there, right? V is the pre-image in Y. So now, I mean, I could just finish the proof in my head. We use continuity of F. We use continuity of F applied to the set V and the hypothesis HV, and there we go. So I've just kind of the fact that I can use the software quite well just means that I can chain lots of steps together. And so I've sort of skipped, I've skipped the rest of it. Now it says no goals. So that's the current state of the brain. If the brain says no goals, that means the proof is done. So that's how you prove, a basic undergraduate level theorem in the way that we prove it to the undergraduates. And of course, and now you're kind of thinking, great. So if it takes 10 lines to prove that composite of continuous functions is continuous, then clearly this isn't going anywhere. So perhaps I should give you another proof that composite of continuous functions is continuous. Let me put sorry again to remove the error. Let me show you another proof that composite of continuous functions is continuous. What I was using here was I was using very low-level tactics. These tactics are these things that enable you to apply the axioms of mathematics in a very laborious way. And what Lean's Maths Library has some extremely high-level tactics. If I want to prove that e to the minus x squared over 2 is a continuous function of x, then I absolutely don't want to prove that from the axioms of mathematics. I just want some all-singing, all-dancing tactic that will prove that an arbitrary function is continuous. And we have that tactic. It's called the continuity tactic. So if I type continuity, then you see I get no goals as well. So that solved the entire, that solved the entire problem, in one line immediately. because this is what we mathematicians have been doing in the maths library. We've been isolating things that mathematicians do, and that actually, if you write them down from the axioms, they take a long time. And we've sort of been working out how to make those much more, effective. So that's what using the software looks like. And then the first question that should be on your mind when you see that is, does it scale? I've managed to prove that composite of two continuous functions is continuous in one line, but can you actually prove sort of a non-trivial theorem at master's level, or can you prove the Poincare conjecture? It's all very well doing undergraduate stuff, but can we actually formalize modern mathematics in real time? And it is a very natural question, and I think for many years the honest answer to that question was no, and now the answer is far more nuanced. So let me first attempt to mislead you by pretending to answer this question by just giving you some data points. And the first data point was in November 2023, 4 mathematicians, including 2 Fields medalists, announced a proof of an old conjecture of Katalin Martin, her polynomial Freiman-Ruggie conjecture. They stuck this 35-odd page paper on the archive. That was 33 pages. And the statement is this: you fix some positive real constant k, and then you've got this vector space of possibly very large dimension over the field with 2 elements, and you take a non-empty subset A, and you assume that A is approximately additive. You assume that A plus A, the size of A plus A means the set of elements of the form x plus y, where x and y are in A, and the naive model for how big that would be, it was like size A squared. You expect it to be size quadratic in A. And let's assume that actually it only grows linearly in A. Let's assume that if you take 2 elements of A, like if A was a subspace, then A plus A would equal A again. But if A was a random subset, then A plus A would have size like A squared over 2. Divide by 2 because it's, addition is commutative. So let's say A plus A is at most linear in the size of A. Then the claim is that A is nearly a subspace. Then there is actually a subgroup of V such that A can be covered by sort of polynomially many cosets of this subgroup. So that's a very tricky problem in combinatorics that was open for decades, and it was resolved in November 2023. And 4 days after the proof was uploaded to arXiv, Tao announced that he was going to run a project formalizing the entire proof in Lean. And the entire process took 3 weeks, and lots and lots of people joined in. It was a multi-author project. 25. I think one of the reasons 25 people joined in was because, like, there's Terry Tao on the internet going, "Who would like to collaborate with me?" And so lots of people instantly say, "Actually, that sounds like a fun thing to put on my CV." So it wasn't difficult to get people to join in. So 25 people joined in, and as a result, the entire proof was read extremely carefully, and all the typos were eliminated, and all the unclear statements were made clear. Right? It was as a result of the formalization process, the paper gets better. It's a minor win, but it's some kind of win. And you can see if I click here, does this? Oh, there we go. There you can sort of see they first wrote a Lean, they first wrote the code in Lean, and then when they'd finished with the code in Lean, they had, is there a blueprint? There we go. They turned this into some kind of graph, and all of these dots correspond to. So you'll have a talk on blueprints in a week or 2 from Pietro. So I won't dwell more on blueprints, but they use a software called Blueprint software. So why would Terry Tao choose to formalize one of his papers like that? I think one reason was he thought it would be an interesting sort of experiment to see if it worked and to see if he could run a largely collaborative project. Because of course you don't normally collaborate with 25 people. But one interesting win that he likes to highlight is that during the process of the formalization, the statement of the theorem had a 12 in. There was sort of at most 2k to the 12 cosets of a subgroup. And during the formalization process, a mathematician who wasn't involved in the project claimed that they could reduce the 12 to an 11. They said, you can reduce the 12 to an 11, you change this part of the argument here, you change that part of the argument there, and everything else goes through. All of the other 33 pages go through honest gov, and the 12 can be changed to an 11. And And the really nice thing about the project is instead of somehow changing the 12 to the 11 and then having to read the entire 33-page project again with this new mindset that the 12 had become an 11, all you had to do with the computer proof was you just had to change the 12 to an 11 in the statement of the theorem, recompile and see what breaks. So it's a much, much more efficient way of finding out if the proof really could be modified to prove this stronger theorem. So that's one advantage of doing mathematics in this way. And in fact, when I was a postdoc at UC Berkeley in the 90s, there was a paper of Ken Ribbett that started with the line, let P be an odd prime. And I spent many, many months of my life trying to work out what went wrong when P was equal to 2. And if I'd have had this software available to me now, I could have just changed, just deleted the oddness hypothesis and then recompiled to see what would happen. Somehow what took me months could have actually taken minutes instead. So that was one example of a high profile recent project. Another example, there was a MSc student at Imperial, my university, currently now doing a PhD at Carnegie Mellon, and he's formalizing Vysovska's proof of 8D sphere packing in collaboration with Vyazovska. So this is the work that won the Fields Medal in 2022. So that's not been done yet, but we're sort of well over halfway through. So we'll do 2022 Fields Medal mathematics. And another thing, there was a recent preprint by some people at the University of Bonn proving a result on doubling metric measure spaces. I should say I don't really know what these things are, but I do know that this theorem, this preprint actually implies a classic old theorem of Carlson about almost everywhere convergence of Fourier series, sort of a famous old result from the 1960s. And this has been completely formalized now. The project took just over a year, and the paper was very, the paper was quite technical, and the whole thing was done in just over a year. So I've told you some data points, and now you kind of, I've sort of tricked you into believing that, well, we can do 2022 Fields Medal stuff there before we can do anything, right? Can we actually conclude from these examples that all modern mathematics can be formalized in real time? And the answer is no, because what we can actually conclude from what I've told you is that some modern mathematics can be formalized in real time. And if I take, I was active in the Langlands philosophy for several decades. And if I look at theorems that people are proving in the Langlands philosophy and the p-adic Langlands philosophy, right now theoretically it would be possible, but in practice it would be extremely difficult to formalize proofs of these theorems, because at the minute we can't even state those theorems. You see, the tau thing, the polynomial Feynman-Rüger conjecture, this is a statement about subgroups and polynomials and and subsets and vector spaces, whereas theorems in the p-adic Langlands philosophy involve the Farg-Fontaine curve and perfectoid spaces and derived infinity categories and all sorts of funny things, and condensed mathematics, which we do have actually condensed. We do have a good theory of condensed mathematics, but there's plenty of things that are missing. Even going back 30 years, a proof of Fermat's last theorem, proofs of Fermat's last theorem use Shimura varieties and automorphic representations, and neither of those things, neither of those definitions are in Lean's mathematics library yet. So it's not as easy, as the example. The examples make it look like it's a massive success story, but the actual truth is it's a bit more complicated than that. And in fact, over the past year or so, I've realized that this is becoming one of the major bottlenecks to formalizing modern research mathematics, is that in many cases, we can't even state the question. And in fact, I wasn't going to mention it in this talk, but now it seems like a natural time to say it. I've just been given, I got some funding from Renaissance Philanthropy, from Renville to formalize statements of theorems of recent annals papers. I've just hired 4 postdocs from across mathematics to be going through annals papers and asking the question, can we state these theorems in Lean? Because that's obviously a much easier question than can we prove them. But can be, for me, for far too many modern papers coming out in top journals, the answer is no, and we need to change that to yes. We need to tip the dial. So what's going on here? What's the vision? Why formalize mathematics? I've just showed that it's sort of possible in some cases to formalize it, but why bother doing it? Because of course, what we should be doing is just getting the open AI to make an AI system which can prove the Riemann hypothesis all by itself, right? And AGI and the singularity, and all, that's clearly what we should be doing. But of course, firstly, I should say that nothing I've said so far has got anything to do with AI. Right? Lean is not AI. Lean is a computer program. And Terry Tao typing in a proof of his theorem into AI into Lean is not AI either. Right? That's mathematicians manually translating mathematics from LaTeX into Lean. Right? It's nothing to do with AI at all. This is all about writing your papers, but in a weird new way, not writing them in LaTeX, but writing them in something else. So why should we be concerned with writing our papers in a new way? Why shouldn't we be concentrating on making an eye that can prove the Riemann hypothesis? And the point is that no one has a clue. If you step away from the hype, those of you that are in California might be sort of surrounded by the hype. I don't know, but right now the bottom line is no one's got a clue how to make an AI which can prove the Riemann hypothesis. The question is much too hard. So why formalize mathematics? Here's my vision, right? Instead of this dream of making AGI and some superhuman mathematical machine, which might come one day, but I can't see a path to it yet. Why don't we instead concentrate on something which is viable? Something which the experts can see a path to. And so here's something that people are now beginning to believe is viable. What about the more modest goal of translating the entirety of known human mathematics into Lean? That absolutely gigantic project is actually now something that it looks like we're beginning to see a path to that. I remember at some point Google announced it was going to scan all the literature. There was a point where you just couldn't access annals of mathematics from 30 years ago on the internet because the papers were just they existed in paper format and no one had scanned them. But now everything is scanned because of a gigantic scanning effort. And now I'm suggesting that that we could start a gigantic digitizing effort. So I want to say something about this more modest goal. And so the first question is, so I'm saying it's viable. Is it really viable? Translating all of human mathematical knowledge into this system, Lean, or any of the other systems. But Lean is just so far ahead when it comes to mathematical definitions that Lean is somehow the natural choice. And then the other question is why? It might be viable, but what's the point? How is this actually going to help mathematics or mathematicians? So how is this going to help? Let me talk about the second question first. I'll come back to the first question later. How is this going to help mathematics or mathematicians? So let me, ChatGPT is a thing, right? Language models are a thing. And at the beginning, if you asked a language model an easy maths question, a times table, if you ask it 7 fours, it would confidently say 28. But if you asked it to multiply two large numbers together, it would just make something up. It would write down a number which was approximately the right length and kind of began and ended with approximately the right numbers. And the numbers in the middle would just be made up. Because sort of next token prediction, the way these language models work, isn't a good way. The correct way to multiply two 10-digit numbers together is to run an algorithm, not to use next token prediction and get some probabilistic model for which digit to say next. There's a disaster. But by 2024, if you ask ChatGPT to multiply two 10-digit numbers together, then it says, oh yeah, that's an interesting question. Let me write some Python code to do that. So it writes, it fires up a Python session, writes some Python code to multiply the numbers together and reports the output. And so now it gets it right. It was kind of annoying because I would go around in 2023 giving talks going, look at these things. Everyone says these things are going to change the world. Look how stupid they are. Here's a maths question. Look at them failing. And then one day I tried this and it stopped failing. So the same is sort of true. So that's about calculations, but the same sort of thing is true with reasoning, right? Reasoning is proving theorems. If you ask ChatGPT to prove an easy theorem, like the theorem I proved earlier in this talk, or an undergraduate level theorem, it'll just rattle off a correct proof, no problem. Because it's seen a lot of undergraduate level material. It's seen it lots and lots of times, and it's sort of on top of it. But if you ask it to prove a conjecture that's at the boundary of modern research, then unfortunately it will occasionally hallucinate, or it will just vibe. It will vibe its way through. It'll say, "No, now obviously this follows," and you ask it why this follows, and it doesn't have a clue. But it's somehow seen humans saying that A implies B, and so it just says that A implies B, but it doesn't have any understanding. So we'll make it might even say A primed implies B. It's seen people saying A implies B under certain hypotheses, and it has no idea if the hypotheses are true because it's just doing next token prediction. It's not understanding or thinking. So it hallucinates stuff, right? And this is a problem, right? Because if you want it to, so let's assume that the proof of the Riemann hypothesis takes at least 10 pages, and let's assume that we have some model that's got a 99% chance of being correct and a 1% chance of hallucinating. And then there's let's say there's whatever 80 lines in a page, and then you try and figure out what are the chances that a language model is not going to make an error in a 10-page mathematical. The chances are zero, right? It's going to make an error, and a mathematical argument with an error is not a valid mathematical argument. So these things, as they stand, these things hallucinate. It turns out that you can't fix that because they're probabilistic in nature. They will necessarily hallucinate. And the fix seems to me to be like, we taught the damn things Python, so let's just teach them Lean, right? This is a very natural next step. But actually, it turns out that the AI people are ahead of us. They've already done this. There are some systems out there that already know Lean. And for example, DeepMind has a system called AlphaProof. It's not publicly accessible. They're working on making it publicly accessible. But this system has it autonomously wrote Lean code, which solved 3 of the 2024 International Maths Olympiad problems. And in 2025, 2 other companies did the same thing. That proves it wasn't a coincidence or a lie or something. It's difficult to, you can't referee that. There's no paper. There's just always blog posts. There's never any paper. This is tech companies. This is tech companies just announcing results. But several companies seem to have reproduced this, and I suspect that by 2027 there'll be lots and lots of open source models that can do this as well. So language models can already write Lean code. And the advantage of a language model writing Lean code is that if a language model is getting, if you ask it to come up with a mathematical argument, or you ask it to translate a mathematical argument that you give it, but it's running every line through Lean internally, if your proof isn't right, then Lean complains, right? Lean doesn't compile. If the thing compiles, then the system cannot make a mistake, you see. And that will be a really big deal because that's taking you from 99% accuracy to 100% accuracy per line. And so that's getting you from 0% accuracy to 100% accuracy per large AI generated math paper, which is going from false to true. That's a big flip. And if we have such a system that, you could give it LaTeX and it could translate it into Lean and then run the thing through Lean and check it compiles, it's also giving us an AI assistant for refereeing, right? So this is, this formalized, it's sort of a game changer. This idea about, getting as good at translation into Lean is, there are lots and lots of big wins here. So, wouldn't it be nice if we could get some system, either humans or computers, to translate? It's going to have to involve computers to translate all of mathematical knowledge from LaTeX into Lean, right? And then we could train on it, and then we'll be able to translate anything from LaTeX into Lean, and then we'll be in good shape. But this question I raised earlier, is this viable, right? I've suggested that it might be very, very, very useful, but is it viable? And so clearly we can't do it manually because human mathematical knowledge is just increasing at some huge rate. So the question is, can we use machines to help us do it? Because that's the natural. So this is about AI. Can we use machines to start helping us? And I've already shown you that actually machines can do baby stuff, right? Machines can sort of manipulate school level mathematics. It's intricate mathematics, but at the end of the day, it doesn't involve any complex objects. Machines can write Lean code at IMO level, but what about the Poincare? The Poincare conjecture is something where we believe we have a proof in the literature, right? We've got papers and books and books on the background and what we believe is a complete and coherent proof that the experts have accepted, are we yet ready to just feed this into the machine and out comes a proof of the Poincare conjecture? So the rest of my talk, that's some overview of what formalization is and sort of where we are. And so now the rest of the talk is really, I just want to talk about is it possible to get the Poincare conjecture all proved in Lean by getting an AI to do it somehow, or getting humans to do it, or getting some AI human collaboration. And here's a subtlety that once you've started using these systems, you begin to understand. But if you're sort of an expert mathematician that hasn't really ever thought about sort of the consequences of typing mathematics into a computer proof system, then this might not have occurred to you. So here's two very similar sounding questions with very different answers. And the first question is, if I have a mathematical theorem and I translate the statement of the theorem into Lean, and then I've got the proof of that theorem and I give it a large language model, and I say to the large language model, you're good at translating, you can translate English into Chinese, why don't you translate this LaTeX proof into Lean, please? And let's say the language model successfully translates this, the LaTeX proof into Lean, and it runs the answer through Lean, and Lean says yes. The resulting code compiles. Do we actually believe now that the machine has translated the proof of that theorem into Lean? And the answer is yes, right? Lean is superhuman. Whenever Lean has said something, I've used the system for 8 years, and whenever the system disagrees with the human, whenever the human says this is right and Lean says this is wrong, Lean is always right. And Lean never says this is right and the human says it's wrong. Lean is just superhuman, and there are various techniques you can use, type checkers and things like this, to get around the fact that there might be bugs in Lean. You can use tools which aren't Lean to verify. Once something is in Lean, it turns into a gigantic directed acyclic graph corresponding to a proof from proof of the theorem from the axioms of mathematics. And you can take that directed acyclic graph and sort of use other programs that aren't Lean. You can say, well, even if Lean has bugs, you can independently check that these proofs are correct. But here's another question. If we give a large language model a definition in LaTeX, and we ask the large language model to translate the definition into Lean, and then we run its output through Lean, and Lean says yes, it compiles. Can you trust the output? And the answer is no, right? And the reason the answer is no is that I know what a modular form is because I'm a number theorist, and a modular form is a function from the upper half plane to the complex numbers satisfying a list of axioms, right? And I could write those axioms down in LaTeX, and I could tell a large language model to translate that definition into Lean, and the large language model could then could garble one of the axioms, or it could forget one of the axioms, right? And at the end of the day, you'll have a function and then a list of 9 axioms that it has to satisfy, not 10, and that code's still going to compile. That's the big problem. The code is still going to compile. It's just the resulting thing won't be a modular form. It will be something else. So there's no guardrails for definitions, right? You could trust the thing. You can trust the thing if it says it's proved a theorem, but you can't trust it if it says it's come up with a definition. So you have to be sort of super careful here. And if you want to embark on a proof of the Poincare conjecture in Lean, then one place you can start, just sort of thinking about what I was going to tell you, and that in particular, that example, one place I think you want to start is you want to think about all the key definitions which are needed in the proof. Because more often than not, you'll find that such definitions are not going to be in Lean's maths library, right? You're going to have to figure out where the library, for example, C infinity functions, they're in the library. C infinity manifolds, they're in the library. Like Riemannian manifolds, I think they just made it a few weeks ago. Like Ritchie-Flow, nothing, nothing to do with Ritchie-Flow. There's like tangent spaces, but there's sort of there's no de Rham cohomology. There's sort of you'll have to figure out where the boundary is, right? And for those definitions which aren't already in Lean's maths library, it seems to me the very first step you need is you want to get those definitions in. So you either get a Lean expert to formalize the definitions, or you become Lean experts and do it yourself. And the reason that you'll have a large success rate in attempting to do that is that's exactly the kind of the material that Lean's maths library wants. That's exactly the kind of stuff that will be prioritized in the review process. So what does running a big formalization project look like? Because the other thing about Poincaré is it's huge, right? And I've watched many projects, from small to huge. And in my experience, the bigger ones are doomed to failure if they don't have a manager. So I'm involved in a project formalizing Fermat's last theorem at the minute, but I don't think that project could possibly succeed were it not for the fact that I've got a grant that buys out all of my teaching for 5 years. So I can work on Fermat's last theorem every day. In fact, I haven't worked on it today yet. I feel quite, because I've been writing this talk. This is why I try not to give so many talks nowadays. But I every day I would like to make more progress on proving Fermat's last theorem, and the reason that I can do that is that my time has been bought out. And I've seen other projects where somebody puts something down and says, look, here's a coherent route to proving this goal. Now off you all go. I've given you the plan. We just need to formalize this paper and this book and this thing here. Off we go, and then it's sort of nothing happens. And even when people are working on it full time, formalization of mathematics can be an extreme. I shouldn't say is. It can be an extremely slow process. And that person who's going to push that project forward needs to be prepared to sometimes move at a glacial pace. And my instinct is that leader should probably be a Lean expert. Maybe I just don't. In all the examples I've seen of successful projects, the leader of the project has been somebody that sort of knew the software back to front. I don't know if that's a necessary condition, but it was that was what was happening for all the projects I've watched in the past. So I think too long didn't read. I think the project needs a leader. So the next question is how much can you get machines to do? So this is auto formalization. I've talked about this already. The process of you give a machine, you don't ask the machine to come up with mathematics all by itself. You give it the LaTeX, and it spits out the Lean. And there's several companies involved with this, but let me just mention Math Inc. because they're a company based in the Bay Area, and they're concentrating on auto formalization. And they, like Christian Szegedy is involved, and he's an absolute leader in the field of AI. He's someone whose opinions you should take seriously, and he seems to think that this is going to be the next big thing. And so where does the tool they just recently announced the proof of the prime number. They fed in a LaTeX proof of the prime number theorem into their system, and their system translated it into Lean. And my instinct is that tools like that are going to be a good fit when you're for the bottom up parts of the project. For example, when you're taking some very, very basic stuff that Lean's maths library doesn't have yet, but there's extremely clear, good documentation. There's sort of standard textbooks that explain things very carefully. I believe that the organizer of the seminar might have written such a textbook when it comes to Ritchie flow. But of course, I've said that you might need a leader, and having a leader will cost time, and time is money. But also, of course, running a language model to translate LaTeX into Lean also costs money. So don't think that you get this for free. It's going to be it might be expensive. So there's a bottom-up approach where you just start by formalizing the basics of Ritchie flow and sort of move on from there. But actually, in some sense, a much more mathematically stimulating approach is a top-down approach, where you see the idea is you don't have to build up from the bottom. Lean's maths library is just completely built up from the bottom. You start with the axioms of maths and you build up to an undergraduate degree. all standard theorems in graduate level, commutative algebra textbooks or whatever. And standard facts about Banach spaces, all completely proved, all from the axioms of maths. But if you're doing a formalization project like Poincare, then you don't have to start at the bottom. You can sort of start anywhere. You have to make sure that sort of when you meet in the middle, everything glues together, and that's why definitions need to go first. If someone has a definition and they assume that something was twice differentiable, and someone else has a definition but they assumed it was infinitely differentiable, and mathematicians are sort of very vague about the the differences and don't really worry about it, and then you glue it together and suddenly there's this mismatch. You can't have two people proving different theorems about the same quotes definition, but it turns out it's sort of not quite the same definition because you weren't careful enough. You want one definition of everything, and then you glue it together. But as I say, in my experience, top-down formalization is far more mathematically stimulating because you start with the mathematically challenging and new stuff, as opposed to stuff that's been known for decades. So as I've mentioned already, I'm running a project to formalize a proof of Fermat's last theorem. And the first step of that proof, the first step of that project is to reduce the proof to a collection of lots of results that were known in the 1980s. So in some sense, I'm formalizing Wiles's paper, because Wiles's paper was the early 90s. But of course, there's a gazillion, Wiles's paper has got a gazillion references. And right now, I'm just assuming all the references. That's a pithy way of summarizing what we're doing. So I spent the first year, this is a 5-year project. I've done 1 year of it. And I spent the first year doing bottom-up stuff, doing a lot of basic definitions that weren't in the library. But now we're working top-down. And finally, let me say something about timing. Like how long is it going to take? Well, my guess is that it's like at least 100+ person years away. That's my guess. Probably more, right? So it's absolutely gigantic. Just like Fermat is also that sort of ballpark. It's an absolutely gigantic project. So the full cost, if you get people to do it all, then it's going to be 20 million. If you get machines to do some of it, then you've still got to pay for the machines. And these LLMs are also incredibly expensive, but maybe ultimately they'll be cheaper. I don't know. But there's some kind of ballpark figure, and that might not, might be twice that or 10 times that. I just don't know, because I don't really know enough about the details and the gap between the actual proof and what's in the maths library, because I'm not an expert in this area. But what I did with the Fermat project was I set this intermediate goal, which was like formalize the Wiles paper and assume all the references, so reduce Fermat to the 1980s, and that's only going to cost $1.5 million, because my university top slices it and then spends the rest of it on my salary. Unfortunately, I don't get paid $1.5 million divided by 5. I get paid $1.5 million divided by 10, and because somehow I don't know, I don't understand how money works, but that's how much it cost the EPSRC, the UK sort of science funding agency, and that will get us. I'm confident that will get us through the Wiles paper, which is a 100-page paper. But on top of that, we've still got 1,000 pages of Grothendieck to get through, and 500 pages of Langland. There's still huge amounts of stuff that need to go in. So maybe we'll do it quicker than 5 years. I don't know, but AI will get better and cheaper over time. So I think this is the last slide. How am I doing for time? Oh, great. I've got time for questions. So these are my suggestions for next steps. So firstly, I think you shouldn't just the goal shouldn't be prove Poincare. I mean, that's obviously the ultimate goal, but the first thing you need to do is come up with a bunch of sub goals, reasonable sub goals which are actually feasible. Because like prove Poincare's conjecture in lean is not a feasible. Oh, I put the accent the wrong way in Poincare. Prove Poincare's conjecture in lean is right now completely unfeasible. Even given the best AI tools or whatever, and given an army, it would still take forever. So you might want to find a more reasonable intermediate goal. So, for example, teach lean something about Ritchie flow. Take a very simple target goal about Ritchie flow. If you want to do bottom up stuff, then think about stuff which isn't in the library and just have very basic. This is what I was doing for a year. We had some very basic theorems about the adels of a number field. These are things that come in the definition of an automorphic form. And I just had some very basic theorems about Adele's of a number field, and we've, in a 6-month period, we've basically proved most of those theorems. So you want to find some basic bottom-up goals, maybe, or some basic top-down goals, if you like. Reduce Poincarés, reduce the proof of Poincaré to hard statements X, Y, and Z. So again, not do the whole thing, but sort of find some goals which are sort of achievable in finite time. Because I'm suggesting that the proof of Poincaré is not really achievable in finite time at this point. And then once you've got some reasonable intermediate goals, you want to find people that will actually run those projects. Some people whose quotes job it is to actually get those goals over the line. I think I do want to stress that it's not always possible to move quickly, right? Some things which are just like the human says it's obvious, or the human says, oh, it just follows from this sort of technical 20-line argument. But that, one extreme example of this, there was some 4-line argument in a paper, no, 5 lines in a paper of Scholzer that took a best part of a year to do in Lean, because he just assumed all of the, he just assumed all of the theory of standard results about derived functors and abelian categories, none of which were in Lean's maths library at the time. And we just had to build them all from scratch. So it's not always possible to move quickly. I think, just thinking about what's needed, I think definitions are the key thing. You really want to get definitions in. You want to find the main definitions and work on getting those definitions, not into your own project. Like the Poincaré project, I could imagine it would be a standalone repository that sort of depends on the maths library. The maths library would be a dependency. But for the key definitions, you actually want to get the definitions themselves into the maths library. Because the maths library, you should regard the maths library as canonical, right? It is it is the standard, like the definition of ring in Lean's maths library is, as far as I'm concerned, now the canonical definition of ring. And we should never make our own definition of ring for whatever reason, because we've got the definition of ring, right? And if you make some definitions relevant to the project, but somebody else independently makes them, and then they PR them to the maths library and they get merged, and those definitions aren't literally exactly the same as yours, then suddenly you've got a lot of technical debt on your hands, because you've now got to start translating between two definitions, right? Find the key definitions and get those definitions into the maths library. And then finally, if you want to start experimenting with what AI can do, because if you don't want to do this, it's good fun to do things manually, but if you want to start getting AI to do it, then talk to one of these companies which are attempting to do auto formalization from LaTeX into Lean, and make sure that you have a really solid, detailed LaTeX description of a mathematical argument whose conclusion is a sub-goal. Make sure the definitions are already in the maths library, because don't ever trust an AI with a definition, right? That was the moral of that earlier slide. Don't trust AI with definitions, and don't trust your friends either. Only trust the definition once it's in the maths library, because then it's been officially reviewed and everything, right? Once those definitions are in, then start thinking about maybe an AI can start doing some proofs for you, and then finally, good luck. That's all I have. So thank you very much for the opportunity. So I have to go at 9 a.m. on the dot, but I will quite happily have questions.
Okay. Yeah, thanks for the very, very inspiring talk. Any questions?
Kevin, I have a question for you. Christian
Yeah.
Popescu here, not in
Oh,
California.
hi.
Hey, it's very good to see you.
Yeah.
Not in California at the moment, closer to you. I'm in Princeton for a little while. So, question for you regarding this project of formalizing Fermat's the proof of Fermat's last theorem.
Typical coming from a number theorist, but go
on. Well, I'm just wondering. So you mentioned hiring some postdocs for this. Money coming from Renaissance Technologies, I understand.
No, Renaissance philanthropy is different.
Philanthropy. Okay. These postdocs, so are they going to dedicate their entire time to this project, or will they have time to think about some new mathematics and publish some things and get a job afterwards?
So I just hired 4 postdocs and gave them the project of formalizing statements and recent annals theorems. And I said, why don't you spend 50% of your time doing that, the other 50% of your time doing what you like?
Okay.
That was what I suggested.
In the process of formalizing, is your feeling that they will learn some new stuff? I mean, stuff that they didn't know before?
Formalizing's taught me a huge amount.
Okay.
But yeah, I don't know. I mean, they're just learning a skill.
Mhm.
They're learning a skill. I mean, I am producing PhD students now that are graduating, and some of them haven't proved new theorems, right? They've been doing translations and thinking about how to teach computers mathematics. But those that want to stay in academia are getting postdocs, because there is money out there. Like Renaissance Philanthropy have funded a project to get the LMFDB into Lean, the L functions and modular forms database. And one of my graduating PhD students has just got a 2-year postdoc, who's going to work with David Rowe and Drew Sutherland, formalizing formalizing the LMFDB. So sort of jobs are appearing, and there are other jobs. There are tech companies which are interested in. This is the weird thing. There are tech companies interested in mathematics. So people can get jobs working for tech companies, but still doing mathematics. And this is, my students seem to be finding this attractive.
Sure.
So, it's not a dead end at all, but it's a weird thing. But, I haven't proved a theorem since 2017 and I've still got my job.
Thanks. I really enjoyed the lecture.
Oh, thank you. Thank you very much.
Yeah.
Okay. Actually, I have another question. So
Yeah.
it's maybe just 1 minute. So when you try to formalize things, do you just go straight to the point, or do you make a more general framework?
Yeah, that's an interesting question. If I'm absolutely, I mean, for small things, if I know the proof, then I might just sit down and write it down. For bigger things, I might sort of write down a proof on paper first, including all the details, and then write that, or write down a proof in LaTeX. This is what you'll see. You'll see a talk about the blueprint software. For this, if you want to do a really big thing, if you want to do a 30-page paper, then the first thing to do is to write a blueprint, and then you formalize the blueprint. So I don't want to give a spoiler for 2 weeks' time. But yeah, for things which you know how to prove already, you can just sit down and prove them. It's just literally it's just like you're playing a computer game. You're playing a computer puzzle game, and the goal of the puzzle game is to prove a theorem, and you just know the proof of the theorem, and you just write down the proof. So then you don't need any planning at all. But for bigger things, you have to plan a certain amount.
Okay. Okay. Yeah. Thank you so much for your time. It's a wonderful talk.
Oh, thank you.
Okay.
Did I spell Poincaré wrong entirely all through the? Oh dear.
Maybe it's to the right.
Yeah. I'm well aware it's to the right. It's just I was typing in LaTeX and not checking, pressing the wrong button on my keyboard.
Well, thank you so much, Kevin, for this truly amazing talk. And
Okay.
we really, really appreciate it. And I guess next week we'll have Professor Zaiwen Wen from Peking University, and he'll be speaking on advancing mathematical formalization, tools and techniques for Lean. Yeah. Thank you
Nice.
so much again, Kevin, and hope to
Yes.
see all the participants again next week.
Yeah, thank you very much.
Thank you.